You know, they're everywhere. They fill the room you're in right now, they're in your car's tires, and they're literally keeping you alive with every single breath. But the gases all around us, they follow a set of hidden rules, these invisible forces that dictate their every move. So today, let's pull back the curtain, make these forces visible, and really get a handle on the rules that are secretly running our world.
I mean, just picture a hot air balloon. It's gigantic, it's beautiful, and it just floats effortlessly, right? But what's actually happening there? What's the secret sauce that lets this massive thing just defy gravity and lift off the ground?
And hey, it's not just these huge epic displays. The exact same forces are at play in things you see every day. Like, you ever leave a bag of chips in a hot car and come back to find it puffed up like a pillow? Well, believe it or not, that's all connected.
So, to get to the bottom of all this, here's our game plan. First, we're going to look at where a gas gets its power from. We'll call it the invisible push. Then, we'll decode 3 key relationships between the major players. After that, we'll find a master key that puts it all together, and finally, we'll see what happens when different gases get thrown into the mix.
All right, let's dive right in at the beginning. What is a gas really? And where in the world does it get all this power?
Well, it all starts with an idea called the kinetic theory of gases. See, the air around you isn't just empty space. It is jam-packed with countless tiny little particles, molecules, that are just zipping all over the place totally at random. Seriously, just imagine a chaotic game of microscopic billiard balls that never, ever stops.
And all that zipping around has a big consequence. Every single time one of those little particles smacks into a surface, like the inside of your tire or a balloon, it gives it a tiny little push. Now, one push is nothing, but multiply that by billions upon billions of collisions happening every single second, and that's what we feel and measure as pressure. It's just the grand total of all those tiny relentless pushes.
Now here's the cool part. To figure out what a gas is gonna do, we really only need to keep an eye on 4 key things. We've just met pressure, which is the force of all those collisions. Then you've got volume, that's just the amount of space the gas is taking up. Next is temperature, which is really just a way of measuring how much energy those little particles have, how fast they're zipping around. And finally, the amount of gas itself. These 4 variables, they're the key to everything.
All right, so now that we know our key players, pressure, volume, and temperature, let's look at the rules of the game. How exactly do these guys influence each other? Let's start with a simple one. Imagine you've got some gas trapped in a syringe, right? And you push the plunger down, you squeeze it. What do you think happens to the pressure inside? Well, as you shrink that volume, you're forcing the exact same number of particles into a much smaller box. They've got way less room to move around, so naturally they're going to slam into the walls way more often. And all those extra collisions mean more force, which means, you got it, more pressure.
And this relationship where one thing goes up and the other goes down, it's so predictable it's got a name, Boyle's Law. It's a fundamental rule. Squeeze the volume down and the pressure goes up. Simple as that, as long as you keep the temperature steady.
And listen, this isn't just some stuffy old science concept. Boyle's Law is happening inside your body right this second. When you take a breath in, your diaphragm expands the volume of your lungs. That makes the pressure inside your lungs drop just a little bit below the air pressure outside, and so air rushes in to even things out. Every single breath you take is a perfect demonstration of Boyle's Law.
Okay, so we know what happens when we squeeze a gas, but what about when we heat it up? Let's go back to that bag of chips in the hot car.
When you add heat, you're basically giving those tiny gas particles a shot of espresso. They get super hyper, they start moving way faster, and they start smacking into the inside of the chip bag with a lot more force. Now, since the bag is flexible, the only way for it to deal with all that extra pushing is for the bag itself to expand.
And yep, you guessed it, this relationship has a name too, Charles's Law. It just says that when you're not messing with the pressure, volume and temperature are directly linked. You heat a gas up, it expands, you cool it down, it shrinks. This right here is the secret behind that hot air balloon.
But wait a minute, what if the container can't expand? You know, think about a can of spray paint or even your car tire. The volume is pretty much fixed. So what happens if you heat that up?
In that case, all that extra energy you're pumping in from the heat, well, it has nowhere to go. The volume can't change, so all that energy just goes into making the particles hit the walls harder and more often. The pressure just builds and builds and builds. This is Gay-Lussac's law, and it's exactly why you see those warning labels on aerosol cans telling you to keep them away from heat.
So we've got Boyle's Law, Charles's Law, and Gay-Lussac's Law. That's 3 different rules for 3 different situations. It's a little clunky, right? What if there was a way to bring them all together into one powerful tool?
So let's just look at the clues we've gathered. Boyle's law links pressure and volume when temperature is constant. Charles's law links volume and temperature when pressure is constant. And Gay-Lussac's law links pressure and temperature when volume is constant. See the pattern? Each law is a piece of the puzzle, but it only works in a perfect lab setting where one thing stays perfectly still. What happens in the real world, where everything's changing all at once?
Well, that's where this comes in. The combined gas law. This is our master key. Just look at it. It brings all three of our players, pressure, volume, and temperature, into one single beautiful relationship. And this is so important because it lets us describe what's happening in the real world, where things rarely stay constant. With this key, we can actually predict what happens to a weather balloon as it rises into the atmosphere, where both the outside pressure and the temperature are dropping at the same time. This is the tool that puts all the pieces together.
Okay, so we have the master key for a single gas, but there's one last piece to the puzzle. I mean, the air we're breathing right now isn't just one thing. It's a mix of nitrogen, oxygen, and a bunch of other stuff. So how do our rules work when you've got multiple gases all sharing the same space?
Well, the answer is actually really simple. It's called Dalton's law, and it basically says that each gas in a mixture just does its own thing. It acts like it has the whole container all to itself. Its particles are zipping around, creating their own pressure, and to get the total pressure of the whole mix, you just add up the individual or partial pressures of each gas. That's it.
Think about a heliox tank that deep-sea divers use. It's a mix of helium and oxygen. To find out the total pressure inside that tank, you don't need some crazy, complicated formula. You just take the pressure from the helium, add the pressure from the oxygen, and boom, there's your total. Each gas contributes its own part, and they just add right up.
So there you have it. From the air inside your lungs to the tires on your car, from a hot air balloon to a bag of chips, these invisible forces are constantly at work, shaping our world. They're not magic, they're just a predictable, really elegant set of rules. And now that you know those rules, I've got a question for you. What else in your world is secretly being controlled by the gas laws?